All right, so today we're going to talk about Riemann sums, but I will talk a very simplified version of it. In their full generality, the idea of a Riemann sum would be that if you have, say, a parabola here, and you want to compute the area under that parabola, just like we've been doing, you could partition this into any subintervals. And you start making partitions, and not necessarily the same size, and eventually you would say you could do upper sums, meaning the ones that are a bit larger. And in this case, I gotta be careful because you see, the one I'm gonna do is I'm gonna take the right endpoints, but you really could go to then the next one. If you want to keep it as an upper sum, you would have to go here, and then to keep it an upper sum. So you would always be bounding the integral above. So that would give you an approximation of the area that is larger, and then you could have a lower sum. And in fact, right here I'm taking the left or right endpoint. You could take any point on the interval, and eventually you would take the limit over all possible partitions, and whenever the upper sums, the limit of the upper sums converges or is the same as the limit of the lower sums, then you have the area under the curve, which would be your integral. So that would be your definite integral. So in that sense, then you would say that the integral, which is going to be the area, is going to be the integral from a to b, meaning a being this endpoint, b being this endpoint, of the function, which I should have told you is y equals f of x, so the integral of the function. And then we say we're integrating with respect to x. This is going to be the dx, the differential. So meaning whenever you wrote it in terms of sums, when I write it, you're going to have f of a height times delta x. So when you take the limit, this is going to turn into your differential. And this would be the limit over all partitions. But in this case, I'm just going to say n goes to infinity. I'm going to do n subintervals of the sum from I equals 1 to n of the width of the interval, which I'm going to call delta xi for each one subinterval, and then f of ci, where ci is going to be any point within the interval. So when you take all those possible limits, and if the limit converges, then you say your integral, your function is integrable, and that will be the value of the integral. Now, what I'm going to do, so this sounds like very, very complicated, but I'm going to tell you how to compute these limits for one specific case. Whenever you take the right endpoints and all your subintervals are of the same width. Otherwise, there are other functions where you would benefit from doing different types of intervals. For example, if you want to integrate under the square root function, that one, if you take uniform intervals, is not really going to work. Or it's not going to be easy to compute, but it's going to be much easier to compute if you take different sizes. But as I said, we're going to focus on the case when we're going to do right sums, so not upper, not lower, just right sums. As we would have to prove a theorem that all of this converge, by the way. But the theorem will give us that we can pick any c sub I. So I'm going to pick just the right endpoint. So we're going to start with that. Let's give an example so we can work on this example step by step, and hopefully that will teach you how to compute these Riemann sums for pretty much any polynomial. Well, we have sums all the way to the cubes, but for the ones we're going to be working in our class for sure. So let's go ahead and look at one parabola, just like that one. So let's say we're going to grab our endpoint. So we don't start at 0, so I give you a little bit more general. Let's say our intercepts are going to be 1 and 4. How about that? So our graph, we're just going to pick one function that satisfies one parabola that satisfies that. and our parabola. Okay, so we have now the function. I had to compute it, so we get the intercept at 1. I was putting it at 0. I want it at 1, so I can give you the full generality. And by the way, we don't always have to compute the areas whenever it's or the definite integrals on the intercepts. It can be just any endpoint, but in this particular case, I want them to be my intercepts in any case. All right, so there, we're going to then start computing our subintervals. So how many subintervals do I want? I want n subintervals. So what is going to be the width of these subintervals? It's going to be b minus a, which is the length of the interval, over n subintervals that I'm going to partition into. Now b is going to be 4, a is going to be 1, so 4 minus 1 is going to be 3 over n. And that's my delta x. So now I'm going to start at 1. That's going to be c0, or c sub 0. C sub 1 is going to be 1, and I'm going to go 1 delta x to the right. So I'm going to have here c sub 1, which is going to be 1 plus 1 delta x. So I'm grabbing one of the subintervals over. So then c2 would be this 1 plus delta x again. So I would go another delta x. That's why it's useful to have them uniform, because then you know what each one of them will look like. So I'm going to have 1 plus delta x, which is the one before, plus delta x, which is going to be 1 plus 2 delta x. 2 delta x, not 2x. And as such, you continue. And so your c sub k, let's see, the kth interval will be 1 plus k delta x. Like that. All right, and what are those? Those are going to be my, if you take c1, c1 would be the right endpoint of the subinterval, and you can pick that height and make one rectangle. Now this rectangle, the height, you see you're in the x-coordinate, you have c1. So in the y-coordinate, you're going to have f of c1. Now for the next one, you have x is equal to c2 when you touch the graph. You're going to have f of c2. So the area of this first rectangle would be what? Would be the width, which is going to be delta x. That's what we picked it to be, delta x for all of them. So the width is delta x. The height is f of c1. So you see delta x1, which would be the same as delta x, f of c1. So this sum would be written just like it appears here, except the delta x will be the same thing. And that's going to be useful for us. So let's go ahead and plug everything into our formula and see what we get. All right, so let's write down the area. Then will be the limit, copying from below, as n goes to infinity, of the sum from I equals 1 to n. I called it k here, so maybe I should call it k here as well. Just change the name of the counter. It doesn't change anything at all. It's okay. And then it's going to be f of ck delta x. Now, I didn't write delta x of k as I have here, because remember, the full generality Riemann sums, you can have any width of your subintervals. We're not doing that. We're picking them to be fixed, because that allows us to compute everything a lot easier. So let's go ahead and plug everything in and see what it looks like. So limit as n goes to infinity of the sum from k equals 1 to n. And now I'm going to do f of c sub k, which is going to be f of 1 plus k delta x. And then, oops, times delta x. I already did the c. Times delta x. And so now we can plug in what delta x is. Delta x is 3 over n. So this is going to be the limit as n goes to infinity of the sum from k equals 1 to n. And then here I'm going to evaluate f at 1 plus k times 3 over n. So I can write as 3k over n. And then here I have 3 over n that multiplies. Now, this 3 over n multiplies everybody. You can factor it out to the outside of this sum. And also, now we can evaluate the function being this negative x squared plus 5x minus 4. Now, the function being that, so we get x squared, so the negative x squared, so negative 1 plus 3k over n squared plus 5 times 1 plus 3k over n minus 4. So wherever I had an x, I plugged in a 1 plus 3k over n in parentheses to have to distribute all the operations that I need to, and I do have to multiply everything times the 3 over n that I had here. I wanted to put in the front. I forgot. I'll do it in the next line. All right, so now it's a matter of foiling this out, and we're going to get a huge expression, but everything will simplify somewhat nicely. So we'll do that. All right, now that we have the space to work with this, we can write it again and FOIL everything out. So this is going to become a little bit big, but just be organized. Just take your time. It's not the end of the world. It looks very crazy, but you just have to take your time and do one step at a time. So for example, here I'm going to FOIL this square. So the square of the first is 1. Now 2 times 1 times, and this is not a minus, I'm just doing 1 times 3 times k over n times 2, so 6k over n. And then times, or so plus, the square of this one, so 3k over n squared, which is going to be 9k squared over n squared. So you see, we just FOILed that expression. We're used to doing that, no big deal. Now let's distribute this one, so 5 plus 15k over n, and then minus 4. That one, there's nothing to do. And barely fit it, but you see, we did one step at a time. Don't get stressed, just do it, and we can get through it. So the next step will be, and the key to getting these ones right is being organized, really. That's really the key. So, and not being worried to write a lot. Do every step that you need to. Don't rush. So right here, you can get negative 1. So right here, I could have done negative 4 minus 1, negative 5. I'm going to write it all out just to make sure that I don't make mistakes. And as I said, now you look for like terms. And yes, it does get time consuming to write everything over and over again, but just until you get very, very comfortable, just write every step as you need. So negative 1 and negative 4, those are like terms. I'm going to go ahead and add them together. I'm going to get a negative 5. Now I'm going to have negative 6k over n and 15k over n. Those are like terms as well. So I'm going to add them together. So 15 minus 6, I'm going to get 9. And lastly, this guy, oh, you see? Plus 5, that was a like term. Oh well, we'll cancel that guy out. So we got this cancellation here. Let's erase it. Because we got negative 5 plus 5 minus 4, it canceled off. And now we get negative 9 k squared over n squared. It simplified quite nicely, actually. Very good. All right, so now what we're going to do is we're going to treat these sums separately. So we have two sums, or the sum of two terms. We're going to separate into two different sums. So the way we're going to do that, we're going to do limit as n goes to infinity of the sum, and 3 over n I need here. Yeah. If k equals 1 to n. It's a little bit compressed there, but I just forgot to write my 3 over n. Then I'm going to have the negative 9 k squared over n squared. And now I'm going to have plus, I'm going to write it again, limit as n goes to infinity of the, I forgot my 3 over n. This time I'm going to erase, not going to try to cram it in there. 3 over n sum from k equals 0 to n of 9k over n. Okay, and at this point, what I want to do is look for all the k's. Ooh, k started at 0? That's, I mean, the first term would have been 0 anyways, but that is incorrect. It starts at 1. Let me erase here. All right, so I'm going to isolate those k's, and the way I'm going to do it is I'm going to grab everything that is not a k, and I'm going to move it outside of the sum. And so this would be 3 over n times negative 9 over n squared times the sum from k equals 1 to n of k squared. So you see, that one I'm leaving like that because I have a formula for it. So I can get rid of that sum and write it as an expression of n, as a function of n rather. And that is going to be quite convenient because then I can take my limit. So again, 3 over n, and here I'm going to pull out a 9n because that's those are the terms that accompany my k. So everything that is not a k, I'm just going to pull out of there. And then I'm going to substitute in my formulas. Remember that the sum of the squares was going to be equal to n times 2n plus 1 times, where's my n plus 1? I forgot my n plus 1 over 6. And this one right here, remember it was going to be n times n plus 1 over 2. Those were the formulas we had before. So we can plug that in and multiply everything, and we get the limit as n goes to infinity of 3 times 9 is going to be 27 divided by 6. In fact, I'm just going to have a negative 9 over 2. Am I doing too much at once? Probably. Let's start multiplying. So negative 27. As I told you, don't rush. And I am here rushing. Divided by 6. And then I have 1n, 2n's, 3n's, n cubed. Okay? And then plus limit as n goes to infinity of, now here I have a 27 again, times n plus 1. I changed the order. And then I'm going to have divided by 2 and 1, 2n's, 2n squared. So I have 1, 2n's, and a 2. 2n squared. 1, 2, 3n's, and a 6, 6n cubed. All right? So now we start looking at what things, or what can we say about this. That looks like a very beautiful board right now. You're like, no, I do not agree. So this n cancels one of these, so I end up with an n squared. So that's the first easy cancellation we can do. This square gets canceled with one of them, so I had 2, now I have just 1. And what else? Well, now we just have to take a look at what's going to happen. Whenever we FOIL this out, you're going to have a 2n squared divided by an n squared. Those are going to be my leading terms. So this right here, maybe I'll FOIL it so you see it. Don't have much space, but I think it's worthwhile doing it one time. Then after you just apply it. So negative 27, and then you get 2n squared, sorry, when you FOIL it, plus 3n plus 1 when you FOIL this out. You can check that. n squared. That's what I had left. But when you distribute this negative 27 and this 6, your leading terms are going to be negative 54n squared divided by 6n squared. What I want to say is you're taking an infinite limit. Oh, you cannot see the 6n squared here. I'm going to write a little bit higher. But what I'm trying to say is this is a polynomial of degree 2, polynomial of degree 2. So the limit is going to be the ratio of the coefficients. So all you really need to know is what the coefficients of the leading terms will be. So this one, on the other hand, will be limit as n goes to infinity of 27 n plus 1 parentheses over 2n. So the leading coefficient, again, degree 1, leading coefficient is going to be 27 over 2. So let's go ahead and erase this side and continue our calculation. All right, so as we said, at this point we just have to take this limit, which is going to be negative 27, or these limits rather, times 2 over 6. Just grabbing the leading coefficients of this polynomial, negative 27 times 2, and then this polynomial has 6, grabbing the coefficients, that's what I get, that's my limit, and then 27 over 2, so plus 27 over 2, which is going to be equal to, you have a common factor 27 over 2 here, you can compute it that way, and you get a, this one's going to be a 2/3 and negative 2/3 and 1/3, so 1/3 of this. Let's see, did I do that right? I have a 2 left over. Yes. This is going to be a 1 and a minus 2/3, so 1/3, which is going to be a 9/2. All right, so unit square, I suppose, because you're doing an area. So there you go. That's how you do a Riemann sum, just using your right endpoint. So do not get too complicated, just do it with that.